1.6 is combinations of functions. Just like you can add, subtract, multiply, or divide numbers, you can do the same thing with functions. So if I'm given a function f of x as 2x minus 3 and g of x as x squared minus 1, I can find the sum. I could find f of x plus g of x by simply adding these two functions together. So 2x minus 3 plus x squared minus 1. I would just combine like terms and end up with x squared plus 2x minus 4. Same thing, I'm sure you can figure this out. So then the difference would be f of x minus g of x. I just have to be careful with my signs here because I'm going to have to distribute the negative through the second piece. So this is really negative x squared plus 1. And so when I combine like terms, I get negative x squared plus 2x minus 2. The product, I would multiply them. So here's a crash course in multiplying, if you don't remember, multiplying polynomials. You have a few options here. In this case, you could technically FOIL. I'm going to stay away from that word just because it doesn't always work. It only works when you're working with two binomials. Anyways, I'm going to do a box method. So I'm going to put x squared minus 1 on the top and 2x and minus 3 on the side. When I do that, I'm going to end up with 2x to the third. Remember, you add the exponents. Negative 2x, negative 3x squared. Negative times negative leaves me with a positive. So my answer here ends up being 2x to the third minus 3x squared minus 2x plus 3. If you need to refresh that, there's a video on multiplying polynomials. It gives you a whole bunch of different options for what way you would do it. And then our last one is the quotient, so f of x divided by g of x. So 2x minus 3 divided by x squared minus 1. That's actually my final answer. However, because I'm concerned about when there's a variable in the denominator, I need to be worried when that would be equal to 0. So I would say f of x divided by g of x is equal to 2x minus 3 divided by x squared minus 1. As long as x is not equal to plus or minus 1, because those are going to be the values that make my denominator undefined. So just the generic overview, if f and g are overlapping domains, then for all values of x in both domains, the sum difference, product, and quotient are defined as f of x plus g of x. I could say f plus g of x, f of x minus g of x, f minus g of x. So I don't need to write it. Those are the same thing. They equal the same thing here. So given these two examples, that 2x plus 1 is f of x, and g of x is equal to x squared plus 2x minus 1, I'm going to find the sum, the difference, the product, and the quotient, and then evaluate all of them at 2. So I'm going to start with the sum here. I start by adding the two pieces together. So I can do two different things here. I can do f of x plus g of x and get my generic f plus g of x. So if I did that, I would combine like terms, 2x plus 1 plus x squared plus 2x minus 1. This whole thing simplifies to x squared plus 4x, and then the plus 1 and the minus 1 cancel. So that actually ends up being f plus g of x. Now I can evaluate this at 2. So f plus g of x is equal to x squared plus 4x. And when I evaluate it at 2, I take 2 and plug it in. So f plus g evaluated at 2, remember I'm not multiplying by 2. I'm saying when I plug 2 into the function, this is what it ends up simplifying to. 2 squared is 4 plus 8, I end up with 12. So I would say f plus g of x evaluated at 2 is equal to 12. That would be my final answer here. My other option is I take 2 and I plug it into f, anywhere I see an x, I get a number. I take 2 and I plug it into g anywhere I see x, I get a number. And then I add those two numbers together. So we're going to talk about some of those examples later. But next up is the difference. It might not be a bad idea to pause your video here and just copy this down. Just for the sake of time, I did all the work and then I'm just going to explain it as I go. So I took the two functions and I was careful to distribute the negative and come up with a value for f minus g of x as negative x squared plus 2. And then all I did was plug in 2 anywhere I saw an x and came up with f minus g of 2 is equal to negative 2. Notice here that I had negative x squared. So they want the negative version of x squared. Once you find x squared, make it negative. So that's how I came up with negative 4, as opposed to, that's different, this, the negative of 2 squared is not equal to negative 2 squared, right? The negative is included in the squared. On the right, it's going to disappear, whereas on the left, it's outside. Okay, so in the next one, you're looking at the product. Again, I did a different form of multiplication for polynomials. I stacked them, but came up with the expression f times g of x is equal to 2x to the third plus 5x squared minus 1. And then I plugged in 2 and came up with a value for f times g of 2 as 35. And the last one here is the quotient, and this is the one I'm just going to save because you want to make sure that if you're doing f of x divided by g of x, you're just being careful with your denominator in that you're making sure you're excluding values that would make it 0. In this case, though, I look at this and I know that I'm going to evaluate at 2. So I'm going to see if I can plug 2 in, and if 2 makes it go to 0, it'll be undefined. Otherwise, I don't care because I'm evaluating at 2. Otherwise, I would need to say here, x is not equal to, and then I would factor the denominator and come up with those values. Okay, so here's what I do. I do f divided by g evaluated at 2. I take 2 and plug it in. And end up with, on the top, 5. 4 plus 1 is 5. On the bottom, I have 4 plus 4, which is 8, minus 1, which is 7. So the answer here ends up being 5/7. Remember, for division, you always need to check your domain. That's what I was talking about here. I should really say factors of 1 that subtract to give me 2. Well, there aren't any. I'm going to have to go to the quadratic formula. So if you need a crash course in that, I also have a video to go along with that. I can send to you, or you can just go to Khan Academy. You can go to Google and review how to use the quadratic formula for that. Another way to combine two functions is to form what we call a composition of one with the other. For example, when f of x and g of x are composed, the composition of f with g is written as f composed with g of x is equal to f, and anywhere you see an x in the function of f, you plug in the whole function g. That's why it's in a different color. I plug g into the function x. So I start on the inside and work my way out. And notice it's not a multiplication, it's purposely an open circle. So if you look back for multiplication, I used a dot, different than the open circle. The open circle is a composition. So basically what you're saying is you take the entire function and put it inside the other. We've looked at evaluating. If you look on your last quiz, right, you had to evaluate the function at t plus 1. That'd be like me saying, if g of x is t plus 1, evaluate the function f of x at g of x. You would just plug in the whole function. So we're going to do a few examples so you don't have to worry about this. So for when it says find f composed with g, for f of x, when that's equals the square root of x with x greater than 0, right? Because we can't take the square root of a negative number. And then they tell me g of x when g of x equal to x minus 1 with x greater than or equal to 1. They just limited the domain for me. But that doesn't have to be the case. It can have an unlimited domain. What I'm going to do here is do f composed with g of x. And I'm going to take my function g of x and plug it in. Right, my original function f of x is the square root. So instead of writing x, I'm going to write the g of x function, which is x minus 1. So wherever I saw an x in my function of f, I plugged in x minus 1. And so my new function is the square root of x minus 1. That's also why I have this domain restriction here, because my domain is going to have to be where x is greater than or equal to 1. Because I have to worry about where is this going to be undefined. This is a function that picks up at 1 and goes this way, right? Remember, it's a parabola on its side and only half of it And that's the only time we need to worry about the domain is when the original function has a domain restriction on it. Okay, so here's an example where you don't have to worry about that. If you scroll down, it says, given f of x is equal to x plus 2 and g of x is equal to negative x squared, evaluate, the first one here, f composed with g of x, and then g composed with f of x. So my first thing, I start on the inside and work my way out. So I'm going to write my function f composed with g of x. Means anywhere I saw an x in the function f, I'm going to plug in g of x. So I plug in negative x squared plus 2. I simplify, f composed with g of x is equal to negative x squared plus 2. Now I'm going to go the other way. I'm going to take the function f and plug it into g. So g composed with f of x is equal to, anywhere I see an x in g, I'm going to plug in the whole function f. So this is negative x plus 2 squared, which, if you remember, is not x squared plus 4. But instead I have to multiply this out. So this is really x plus 2 times x plus 2, which is x squared plus 4x plus 4. So it's equal to negative version of that. So g composed with f of x is equal to negative x squared minus 4x minus 4. So if you look at the bottom, it says, note, f composed with g of x is not equal to g composed with f of x. Right? These two things right here are not equal. It does matter, order matters, but what all I was doing was taking g in this case and plugging it into f, and then here taking f and plugging it into g. So I start on the inside and work my way out. Because you could have multiple versions. If I had 3 functions, I could have h composed with g composed with f of x, and I would take x and put it in f, and then I would take that and put it in g, and I'd take that answer and put it in h. We're going to do plenty of examples of practice with this. So like down here, we're talking about finding the domain and then doing examples, identifying composite. We're going to talk about this. This probably is the most difficult of the functions, operations with the functions to grasp, but we're going to spend time doing a lot of practice with it. It's also necessary that you understand this and know how to do it. This is how we're going to prove functions are inverses of each other in 1.7.